In this video, we're going to talk about the integrated rate law. And what the integrated rate law is it's a way we can have an equation that tells us what our concentration is going to be at a certain time point if we know the rate of our equation or the rate order. And we need this because the rate law we talked about in the previous two videos, those only really tell us the relationship between rate and concentration. And inside a lab, we really want to know how our concentration is going to change with time based on what type of reaction we have. And so let's take a look at these integral order rate laws. We're going to start with the first order reaction. Remember, the rate law for this is Ka raised to the power of 1. Well, our integrated rate law for this is the natural log of A equals minus Kt plus natural log of A initial. And so if we graph the natural log of our concentration of A versus time, what you should get is a straight slope. So where this line hits the y-intercept, that is how much A we started with, and our slope is negative K, and K is this rate constant we first talked about in the first video for this chapter. And the rate for first order is molarity per second, because our rate equals molarity per second. And so our K needs to be equal to second minus 1. And let's take a look at why this is. So our rate is how much molarity changes per second. Well, A is in concentration. Concentration has units of molarity. Therefore, for this to be a true statement, K has to have units of inverse seconds. Let's look at a second order rate equation now. Remember, second order is K equals A squared. And so our integrated rate law is 1 over the concentration of A equals Kt plus 1 over A initial. So here again, our y-intercept is 1 over A initial. Our slope is K, our rate constant. Now I have a T1/2 here, and I'll talk about what that means in a minute. But let's think about the units of K again. Again, our rate should have the units of molar per second. A squared means that has the units of molar squared. Therefore, for this expression to be correct, K has to have units of molarity inverse multiplied by seconds inverse. In the case you don't know what these inverse means, it just means 1 divided by molarity. That's what raised to the power of minus 1 actually means there. In zero order reaction, a zero order reaction is we plot A versus time, and we get A equals minus Kt plus A initial. Here our slope is minus A. Since anything raised to the 0 power is 1 and unitless, our rate constant K needs to have units of molarity per second now. Alright, so that was the integrated rate law. Now let's get to the idea of half-life. A half-life is the amount of time it takes for the concentration of your reactants to be half of what it started with. And this half-life, the time, depends on the order of the reaction. So let's take a look at the half-life for first order reaction. So if we start at a concentration of 1, our first half-life is going to be at a concentration of 0.5 because that's half of 1. Our second half-life is going to be at a concentration of 0.25 because that's half of 0.5. Our third half-life is going to be at 0.175 because that's half of 0.25. And we just measure how long it takes to get to these half-lives. So the first half-life is 100 seconds. The second half-life is 200 minus 100, which is 100 seconds. And the third half-life is 300 minus 200, which is 100 seconds. So we see for first order reaction, it doesn't matter how much stuff you have at any given time point, your half-life is always going to be the same time. And here on this table is more or less a giant table that tells you everything you need to know from this video. One, it tells you the rate laws, it tells you the orders, tells you the units of K, it tells you the integrated rate law, it tells you what type of plot you need to plot to get a straight line, and it also tells you the equation for the half-life. So for zero order, half-life is 1 divided by K multiplied by an A initial divided by 2. So you see zero order half-life does depend on the amount of A you start with. First order half-life, 1 over K, remember K is rate constant, multiplied by 0.693. So half-life is not dependent on concentration here, it's only dependent on K. And second order, 1 over K divided by 1 over A initial. So for second order, time, the half-life is dependent on the amount of A you start with. And so what's the point of learning those straight line plots, the integrated rate laws we just talked about? Well, in an experimental setting, or if you just have experimental data, you can determine what order your reaction is based on if you get a straight line or not. So if you have concentration and time in a table, you can plot that on different graphs. So if you plot A versus time, ln of A versus time, or 1 over A versus time, only one of these plots should give you a straight line for your data. And that straight line will tell you the order of the reaction, whether it's 0 for A versus time, first for natural log of A versus time, or second for 1 divided by A. And that's it for this video. I'll see you in the next video.